Good morning, ladies and gentlemen. Thank you for coming and joining in the CCUS conference. There are a lot of tropes around the topic of CCUS. The fact that it's quite expensive, the technology is not developed, but the reality is India will need to develop CCUS, and CCUS will account for close to 25% of the decarbonization emissions by 2070, right? So it's an essential cog in the wheel. And today I am joined by an expert panel who will be sharing their insights on different aspects of CCUS. It's quite heartening to see the kind of progress we are making on this topic. So without further ado, I would like to invite Mr. Nikun Jain to talk about his study.
Thank you, Manan, for such a good start and good morning, everyone. Friends, before starting this presentation, I just want to understand how many of you know that what is our target for the net zero, India target? It's, yeah, anyone? It's 2070, correct. And what is the target for the CO2 reduction by 2030? The India government has made some target. It's a reduction of around 1 billion ton. So my topic and my whole presentation will revolve around this achieving these two major objectives. This will be my agenda. We will discuss first the CCUS value chain. Then we will understand why decarbonization is paramount through CCUS. Then we can just have an overview of the different carbon capture technologies which are presently available and which are being commercialized at the large scale. Then what are the different methodology for the CO2 utilization? The very well-known fact is CO2 can be captured and it uh, can be sequestrated to the underground and can be do EUR. But we will talk more on utilizing it into other different chemicals and petrochemicals. And finally, we will have the brief carbon cost overview. So friend, this is the CCUS value chain. As you can see, we can capture the carbon from the fossil or, or from the different industries, and this can be transport to the through pipeline to the location where it is where we can call as a CO2 sink. After capturing the carbon, the most important thing is at what pressure and temperature it is required to go to sink, because it is all based on which application it is going to be utilized. And finally, the disposition of the CO2 to the different utilization method. The very well-known method is enhanced oil recovery, where we can utilize high pressure CO2 for taking out the crude oil from the underground. And also we have the food and beverages applications. And the most important is we can definitely convert the CO2 into a green methanol or into a urea and different chemical products. So why decarbonization through CCUS? CCUS offers the known technology which for industries which are hard to electrify. Nowadays we talk about the renewable energy, but this is only for the electricity part. The part which is very hard to electrify, such as steel, cement, oil and gas, for that CCUS is the only, what we can say is the only option. It is a sunrise sector for the coal gasification and the low carbon hydrogen economy, where CCUS can be utilized for making the blue hydrogen. So one will be the green hydrogen which is going on, which is coming to a very relatively very costly, but CCUS can be utilized for making the blue hydrogen. In India, nearly 2/3 of the India's steel capacity and around 200 gigawatt of coal-based power plant have the age of less than 15 years. So we just cannot wish out that it can be all green. So only thing, we can run this plant and we can capture the carbon and utilize in an efficient way. So where will be our key focus area? This industry, steel, cement, oil and gas, thermal power station, coal gasification, hydrogen production. And these are the different, steps, or you can say the technology for we can capture the CO2. You can capture the CO2 through the chemical solvent based on the partial pressure. You can utilize either absorption technology, adsorption, or cryogenic separation. And finally, our intention is we must have the value added product from the CO2, like polymers, chemicals, building materials also. So these are the brief overview how the carbon capture technology looks like. One method is you can capture the carbon before combustion, what we call as a pre-combustion CO2 capture. Second is we can capture the carbon post-combustion through the flue gases. The difference between pre-combustion and post-combustion is you can have more percentage of CO2 in the pre-combustion technology as compared to post-technology. And third is the oxy combustion, where you intentionally have the more CO2 content and you will be firing only oxygen, and that will be the CO2 capture having the greater percentage of the CO2, what we call as a oxy-fuel combustion. So these are the brief of the one is very well known as solvent-based absorptions, where from the flue gases you can add the solvent and you can just absorb it and you capture the carbon. The fundamental principle for this selective absorption of CO2 is the fundamental principle. And solvent-based CO2 capture technology works with either you can have a chemical absorption or physical absorption. The next technology revolves around adsorption. CO2 molecules can be adsorbed to the adsorbent material, and as well known that adsorption are based on the different three steps. First, CO2 gets adsorbed on the surface of the adsorbent material. Then there is a diffusion of the other gaseous material through the adsorbent material and exit from the system. CO2 desorption from either decrease in the pressure or increase in the pressure. This we called as a pressure swing adsorption or temperature swing. So these are the different methods where you can have the adsorption through adsorption of CO2 and basically the capturing of the CO2. Adsorption, then second step is a co-current depressurization, counter current depressurization, then purging, and finally the pressurization. The one which is very economical when we want to capture a large percentage of the CO2, that is more than 1500 tons per day or 2000 per day. The technology which is most commercial, which is most economical viable also is cryogenic separation. In this, it is similar to the distillation process, where the separation of the CO2 is based on the boiling point range. The only difference is that the distillation takes place to the sub-zero temperature, that is around lower than the minus 50 degrees Celsius. So this is the comparative analysis of the CO2 capture technology. As we can see that there is a chemical solvent. The advantage of the chemical solvent is there will be the high absorption at a low partial pressure of CO2. So suppose you have low partial pressure of CO2 in your feed stream, we can go with the chemical solvent. And the cons for this will be, obviously, it will be a high energy requirement for the solvent regeneration. The next is a physical solvent method. It is suitable for the gas stream which is having the high partial pressure of the CO2. And it is governed by the Henry's law, which is nothing but, you absorb the more concentration will get absorbed when you have a higher partial pressure. The next is the adsorption. This is applicable and selective only for for the batch process, for the R&D trials and for the lab test. And fourth one is a cryogenic separation, where you need to capture selectively CO2, and if you want to have more high purity of CO2 like the food grade CO2, then we must go for the cryogenic separation. Now coming to the most important part, we capture the carbon, we capture the CO2 from the flue gases available from the what different chemicals and other things which you can think of making it from the CO2. We can definitely, and all the technologies are also available. We can make methanol, we can make ethanol, we can make soda ash. Then there is an polymers, range of polycarbonates are available where we can make it from the CO2. Then in fertilizer area, it is well known that CO2 is utilized in the urea manufacture. In the building material, nowadays CO2 is getting, binded to the concrete material, and it has been established that its strength has been increased. So it is been utilized in the building material, and it is used as an aggregate and the concrete and cement material. Then CO2 is being used as enhanced oil recovery. It's very well established globally. Then heat transfer fluid and others like food and beverages, then that's Pepsi, Coca-Cola, all industries, they want a food grade CO2. So applications and technologies are very well established for the CO2. Now coming to the very important question, what will be the cost for carbon capturing? Now I've just gone through and we have a different market survey like GEC, SSI, National Petroleum Council, EIA, and when you see the chart, the carbon cost capture from the different sector, it is a different. And when you see the average cost part, it is around $60 per metric ton of CO2 when you capture it from the hydrogen SMR unit. It is around $90 to $120 in the cement sector. And capture cost from iron steel sector is around range from 70 to 175. It is all due to what is the composition of the feed source, what impurities are there in the feed source, and what percentage of purity you required for making the CO2. This is a practical, and this is a established picture of the well-known project like Boundary Dam project. The source is a coal gas plant and a Petronova project. As you can see, I just it is red line has been marked. It's around $45 per metric ton of CO2. So some companies can capture the cost at around $60. Some companies are having the cost of around $100. So now our focus, our R&D focus, our government is also implementing some technologies and incentives and PLI, public-private partnerships, for making this carbon cost lower, so that it can be make more viable and more economical. It makes more economical sense to make specialty chemicals and petrochemicals. So thank you very much for the patient hearing. Thank you.
Thank you, Nikunj. I must say it was quite a insightful discussion on the basics of CCUS, right? What are the different options we have? Very interesting trivia. While Nikunj talked about the cost of CCUS, the reality is at around $60 to $80 per ton. Really, the carbon credit does not justify it, right? So today, if you look at European carbon credits, which are close to around $70 to $80 per ton, thankfully it has come back. Even then, CCUS will need some form of green funding, and that has been one of the key reasons why we as a nation have not been able to at least start one key big scale CCUS hub. But then we also have a silver lining. Let me call on stage Mr. Jorge. Jorge is joining us from Venezuela, and he's going to talk about what we think is going to be first of its kind CCUS project in India. Mr. Jorge, over to you.
Thank you, Sherman. Thanks to all the organizers, and thank you everybody for being here this morning. And also I would like to thank Oil India for the support during this project, and actually I'm inviting everybody to visit their booth to know more about this project and other initiatives regarding carbon emission reductions in India. So today we are talking about the feasibility of the subsurface storage of CO2 in northwestern India. It's following the presentation that we just watched. So what we do after we capture the CO2 from different sources, and how we store that CO2 safely. So we are talking about that today. So this is a feasibility project that included the screening and ranking different reservoirs, including hydrocarbon-bearing reservoirs and aquifer in Northwest India. The idea is to select the best candidates for a safe and reliable storage site. The project also included the estimation of the requirement in terms of facilities at the surface, and also the requirement in terms of monitoring and verification. So after the screening and selection of the reservoir, we did a very detailed subsurface identification and characterization. And then we did a conceptual design of the facilities. The conclusion of the project is that we selected two aquifers, of which one is the main candidate based on their characteristics. This project will offer a combined storage capacity of about 15 million tons. The initial plan will include injecting about 80,000 tons of CO2 per year, but the capacity could be up to 350,000. The initial plan include taking the CO2 from a membrane separation unit. So that is one of the technologies that we saw in the previous presentation. We will take that CO2 into the storage site via a 4 inches pipeline long 9 kilometers. So for this project, we need to integrate all the data that we have regarding subsurface. That include pressure, temperature, porosity, other rock properties. Every well data that we have, like well logs and sidewall cores and everything. So, and then we do a first characterization of which data we have. For this project, we have a very good data set, given that this area has been produced for many years. However, we have limited data for the aquifer, especially for the injectivity. So for that reason, the project also included an uncertainty analysis. This is more or less the workflow that we follow in this project, but that is also a standard practice within Gaffney Klein Energy Advisory at Baker Hughes. So basically, we integrate the seismic data with the petrophysicists and the geomechanics data to generate the static models, and then the dynamic simulation model that basically is a characterization of how the CO2 will react at the reservoir, and how the CO2 will move after an injection. With that model, we create also sensitivity analysis and forecast different scenarios. And that model is also used to design the facilities that we will need, and of course, estimation the cost and the techniques that we will use for monitoring and validate the project. In terms of the geological model workflow, as I mentioned, we use all the well data that we have and the seismic data, and we generate an static model that basically includes all the characteristics and properties of the reservoir, and that is the input model that we use for doing the simulation model and the dynamic forecast of the CO2 storage process. In terms of geomechanical is very important because one of the main objectives in a CO2 storage project is to contain the CO2 in a safe way, and that includes avoid any potential leakage, especially due to rock fractures. So for that, it's very important to characterize properly the reservoir in terms of geomechanical properties, especially the seal rock. That is one of the main components of the system. So for that reason, we do the characterization of the geomechanical properties of the reservoir. We use that as a limit for our simulation pressure and the injection pressure, sorry. What else we have in a project like this? Well, we have, of course, the storage side, and but then we need also the capture technology that we will use, and also the transportation from that capture site to the storage site. Um, we designed and we did the conceptual design, but we also need to understand the feasibility of that project. And the main component of this system are the reservoir, of course, the type of well that we will use. Remember that these wells are different from conventional oil and gas wells, especially because the CO2 reacting with the water create a very acidic environment. So it's important to use metallurgy and material for the wells that are CO2 resistant. So we need also the surface solutions, like compressors or pumps or any other facilities. We need also to understand the risks and to understand what control mechanism and tool we need for predicting the not only the CO2 risk and during the operation, but also after 200 or 1,000 years after the CO2 injection cease. And finally, we need to understand the economics of this, that at the end is one of the most important parts of any project. So as I mentioned, the first part is characterized with reservoir we have and what kind of field, and we need to understand the three basic the parameters, so the injectivity, the capacity, and the safe containment. So for this reason, we have to understand how easy it is to inject in these reservoirs and what is the capacity of the total capacity of or volume that we can store. And finally, how reliable and safe is the injection in that site. So we selected 5 reservoirs and we studied 5 reservoirs and ran them. And finally, we selected 2 of them to follow the study and design the facilities. That, as I mentioned previously, that include a seismic characterization, that include selecting the input data, understanding the characteristics of the reservoir, and also to understand the characteristics of the sill rock. That is basically the reservoir that is above our injection site and basically act as a barrier to any leakage to the surface. In the definition, we take not only characteristics of the reservoir, but other aspects like how is the surface in that area, if there is any other activities for gas or oil production nearby, and also political and economic decisions, because sometimes we have the reservoir are located nearby other blocks or even other countries. So we need to understand not only the best characteristics for the subsurface, but also the other aspects that influence the project. As I mentioned, the geomechanics is important, so we have 2 phases in the geomechanics. In the first phase, we try to understand the characteristics of the sill rock and on the reservoir to avoid any fracture. And at the first phase, we only do a 1D model, but then in the second phase, we did a 3D model that we integrate with the dynamic simulation. And that is a two-way couple simulation that is basically an interaction between the injection and reservoir pressure with the changes in the geomechanical and reservoir properties. So as I mentioned, we focus in 2 reservoirs in one of the 3 fields that we have. The selected reservoir is a 3-way deep closed structure. It's about 2,000 meter depth. As I mentioned, yeah, the selected reservoir offer a high permeability and a thick seal rock that offer excellent solution for the permanent storage of the CO2. Um, yeah, we can. This is quite technical, but basically, this is the first. This is about talking about the static model. That is the input model for the dynamic simulation. As I mentioned in the dynamic simulation, we take into consideration the maximum pressure that we can inject based on the geomechanical results. And we use also the phase and rock interaction, especially the relative permeability, because that dictates how quick the CO2 can move into the reservoir and in comparison with the water. These are the results we see here in the low right hand side, how the CO2 have moved around the well after 40 years of injection. We see that the CO2 is contained in a very small space around the well. As I mentioned, we included also a study of the integrity of the legacy well, but also in the future wells, how we design these wells to make them reliable and for a CO2 environment. And also the surface facilities, as I mentioned, after we capture the CO2 from a membrane separation unit, we need to transport that CO2. So we will do with one single 4 inches pipeline, long 9 kilometers. The initial plan is to inject about 4 million cubic feet a day. That is about 80,000 tons a year. But the capacity is quite high. We can inject to 4 times that. We will use also carbon steel in the pipeline. We need also an injection well pad where we'll have our 2 injectors wells and plus the monitoring wells. And finally, this is one of the most important part in every single CO2 storage project. We have to understand also the risks. So we need to do a early risk assessment, rating these risks and define monitoring technologies for the definition and long-term verification of the project. Yeah, thank you everyone for your attention.
Thank you, Jorge. Looking at some of your graphs, I'm sure this must be an engineering marvel. The kind of complexity and the kind of integrity that you would require for this kind of a project. Quick trivia before we move on to the next speaker. So, what is the world scale size of the biggest CCUS project globally? Any idea? So, as we understand today, the biggest commercially scalable CCUS hub is close to around 10 million tons, right? Now, for reference, India's emissions are close to around 3 billion tons, which means that by 2070, we would need close to around 30 to 50 such mega scale CCUS hubs to be commissioned in India for us to go to net zero, right? That too only accounting for like 20% of global, of India's emission. So there is a big pathway for us to traverse, and it's therefore quite important for us to start at least a pilot scale of CCUS. One of the key aspects of commercially starting a CCUS hub is not just the carbon capture, but also how you transport it. And today we have on the same topic of how you transport, Mr. Abhijit and Partha, who will be sharing their insights on what it takes to transport CO2 for CCUS. So over to you.
Hello and good morning. I think I'm confused whether it's good morning or good notes. Almost at the verge of morning and afternoon. So today, my name is Partha. I'm a pipeline engineer by profession. With me is my co-presenter Avijit, who will be taking through some aspects of the presentation. And along with us, other members who have contributed to the presentation is Dr. Pratik Bhattacharya, Ubaidullah, and Bunfei Chang. And on behalf of the team, we'll be sharing our presentation, Flow Assurance and Pipeline Design Consideration for CO2 Transportation. Just a bit of disclaimer, the presentation today is based on a recent design activity that we have carried out for one of our stakeholders, and also the lessons learned from Shell's legacy CO2 pipelines. So though we have tried to anonymize the data and kept it very generic, but would still request that the figures and data included the presentation not being referenced externally, just to respect the non-disclosure agreement that we have with our stakeholders. With that, a brief context setting, I think things has been made easier for me by my previous speakers. So the per capita CO2 emission of India is basically below half of the global average, but in terms of gross CO2 emission, India stands third, just behind China and US. As a member of United Nations Framework Agreement for Climate Change, and also as a societal commitment towards sustainability, India has set and committed a decarbonization path, as shown in the slide, reaching net zero by 2070. Apart from other initiatives like the renewables or green hydrogen or low carbon solutions, we believe that carbon capture, utilization, and storage is an essential imperative for India to meet its decarbonization goal. So this is a typical flow path of CO2 flow line. I think we have seen that different aspects of this flow path being discussed earlier by the previous presenters. So carbon capture, utilization, storage is basically the process of capturing the CO2 from various sources by processes like pre-combustion, post-combustion, and oxy-combustion. The captured CO2 is then transported for use in industry, enhanced oil recovery, or for a long-term storage called sequestration in a geological formation like a depleted reservoir or a saline formation. So as you can see, there are various modes of transportation. The best method depends on factors like how much distance you need to transport, the phase of the CO2 in which you are transporting, and the throughput or the volume of CO2 that you need to transport. The transportation by road or railway is often found to be 3 to 10 times costlier as compared to pipeline per ton of CO2 because of the economies of scale. For long distance transportation beyond 1500 kilometers, even ship transportation is found economical and competitive, but has got associated logistics and HSSC issue transporting refrigerators, semi-refrigerators at pressurized condition. Pipeline transportation is found most feasible and economical when the CO2 is transported what we call as dense supercritical phase. The CO2 stream is typically above 74 bar and 31 degrees centigrade, which we call as a critical point, where the CO2 is a supercritical form, behaving as with density similar to gas, liquid, and viscosity similar to gas, thereby minimizing the frictional loss across the pipeline and the maximum efficiency flow through the pipeline. So CCTS is an acronym which stands for Carbon Capture, Transport and Storage, and often used interchangeably with CCUS, thus signifying the importance of the transport function in the overall CO2 value chain. In our presentation today, we will basically focusing on the transport of CO2. So what are the key challenges of a CO2 pipeline or the design considerations? First is the metallurgy and the suitability of the pipeline material to the flow stream and the impurities in CO2 stream. Second is safety and environment, then followed by compression pumping, and last but not the least is the fluid characteristics and phase behavior. The challenges that I've mentioned is not in order of priority. For the quantity of our presentation today, we'll be discussing the freshest challenges towards the end of our presentation, which my co-presenter Avijit will talk through. So this is the pipeline substance definition that we have arrived at for the representative pipeline that I had mentioned before, based on the various flow assurance studies, the design calculations that we have carried out. Our pipeline length is roughly 14 kilometers, and based on the flow assurance studies, we have arrived at a pipeline size of 18 inch, and it is transporting 3 mmTPA CO2 in dense supercritical phase. And the material selected for this pipeline is carbon steel, API fiber X60, for a design pressure of 135 bar. So coming back to the design challenges that we have mentioned before, the first and foremost challenge is basically the material selection. The impurities in CO2 stream has the potential to combine together and impact the thermodynamic behavior of CO2. And in the worst scenario, it may result into free water solidification or corrosion, resulting in impacting the integrity of the pipeline. So despite that, there are alternative materials like CRA or non-metallics, but non-metallics are not recommended because of the soiling and rapid decomposition issues. CRA is cost prohibitive for a long distance pipeline. So for our pipeline system, we have still gone ahead and used carbon steel for the cost benefit. However, we need to ensure that the CO2 stream is basically dehydrated. And in our case, the water content is less than 50 ppmb. The next issue is basically in a typical CO2 pipeline, you will come across this phenomena called rapid ductile propagation. So because of the phase behavior of the CO2 and also the typical operating parameters to keep it in supercritical phase, we come across this the phenomena of running ductile fracture. To avoid that or to mitigate that, you need to ensure that the pipeline selected material has got adequate thickness. Also, the geometry or the thickness of the material acts as a barrier for the ductile propagation. We have used the brittle to curve method as a guideline to select our pipeline thicknesses, which has been referred in different industry standards like ISO 27913. So in the course of our calculation, we found that the thickness that we have arrived at based on the barrier to crack propagation is governing thickness instead of the hoop stress. That is typically the thickness determination for a pipeline. So if you realize that going for a high grade material doesn't help, because the most optimum the material grade that is X60, and we have landed up at an X60 as our pipeline thickness calculation, selected material grade. The next aspect is safety. So how does CO2 pipeline safety differ from normal carbon steel or hydrocarbon pipelines? In hydrocarbon pipelines, the safety aspect is dictated by radiation or flammability, whereas CO2 itself is non-inflammable. It is available in the environment, generated by human body. So often there is a tendency of normalization of the risk. However, CO2 is asphyxious. It is denser than air, 1.5 times heavier, colorless, odorless. So CO2 available in the atmosphere may remain undetected and may cause different types of health issues, like starting from at very low concentration, it may rise to headache and dizziness. But as and when the concentration increases, it may rise to rapid breathing problem, breathing issues, suffocation, and even in extreme cases, coma or death. So we need to ensure that we carry out some sort of a dispersion modeling and safe contouring when routing the CO2 pipeline, and especially in the high consequence areas. And also, we need to ensure that there should be provision of block valve stations to limit the inventory of CO2 that can be released. Over to you, Abhijit, for the rest of the presentation.
So thanks, Partha. Hope I'm audible. So Partha kind of spoke about the safety and material considerations that go into pipeline designing. So in remainder of talk, I will focus on flow assurance part. And when we are actually speaking of pipeline designing, we are trying to size a pipeline. And for that, we basically need some inputs or information. And here I list out key pieces of information that you need for pipeline design. So the first comes that you need to be aware of the flow rates that pipeline will witness over its lifetime. So specifically design and turn down flow rates. Next on the list is ambient temperatures that pipeline would see, especially during summer and winter months. And if pipeline indeed happens to be in a buried format, you need to have thermal properties of the soil in the local geographical area. Feed composition, as Partha also pointed out earlier, is very important, and specific to CO2 processes, it's the impurities, and I'll touch upon this point in the upcoming slide. And lastly, we need to have good idea of what the pressure and temperature conditions are supposed to be at the end of our battery limit. That's the arrival pressure and temperature. And at this point, I would like to re-emphasize that when we speak of transporting CO2 from both economical as well as operational perspective, it's important to transport it in supercritical phase or dense phase, just to avoid challenges that are associated with two-phase flow. So I'll take a moment to introduce you to the PT curve typically associated with pure CO2. As with any pure component systems, with pure CO2 you have a solid saturation line separating your liquid and vapor phase. So when you are transporting pure CO2, essentially it will always stay in a single phase. It can always be treated as a single phase transport. However, when you have traces of impurities, it does some fascinating things. First is it kind of shifts your critical point, be it specifically critical pressure as well as temperature. And also what you would see is that now the single solid saturation line has blown to a phase envelope, a narrow phase envelope rather. So if your operating conditions are supposed to be located between the blue and green curve over here, you have risk of operating your pipeline in a two-phase flow, which is not very desirable. And lastly, I would like to draw your attention to the red curve, which I show over here. It is it's hydrate line. So whenever you are operating your pipeline, you should always make an effort that you are on the right part of this red curve. So I will quickly jog down through some of the pipe sizing activities that we pursued. So we use steady state simulations run in PipeSim multi-phase simulator. And as far as equation of state is concerned, we use something called cubic plus association. And let me re-emphasize over here, we are basically targeting to operate our pipeline in supercritical region. And for that, we went by few heuristics, namely velocity limits, arrival pressures and arrival temperatures. And as a safety margin, we take place a 10 bar margin for arrival pressure and 5-degree margin for arrival temperatures. So I won't go in detail through these results, but the message that I would like to convey over here is that we went through the bookend cases at design and turn down flow rates, simulated both for summer as well as winter conditions. And we tested two pipe sizes, 16 inches and 18 inches. And we basically ensured that it satisfied all the criteria that I showed in my previous slide. And based on our modeling activities, we reached to a conclusion that 18-inch pipeline was apt for this particular pipeline routing. So far I have spoken about the steady state simulations, but during the lifetime of your pipeline, it will go through many restarts, shutdown, and many transient processes. Now, what these transient processes do is, suppose if you were to hit temperature condition limits such that water can drop out and it can lead to some corrosion issues. You can also, if PT conditions are conducive for hydrate formation, then it can lead to flow issues. And suppose if you were to depressurize your pipeline suddenly, you can, because of Joule-Thomson expansion, you can have a sudden drop in temperature, and you will be in a very dreary state if it goes below your design temperatures. So over here, I will quickly showcase one of the cases that we simulated in dynamic modeling tool Olga, and that's specifically for depressurization. So our starting condition for depressurization is such that we leave our pipeline in a shut-in state for 60 days. And over here, I would basically like you to focus on red curves, which are basically liquid holdup. What you would see is that at the lowest point in the pipeline routing, marked by black curve, you see some significant liquid accumulation. And now suppose if you were to impose a slow depressurization strategy over it, this is how your profiles would look like into the 9th day of depressurization. So the place where you had liquid accumulation marked by red peaks, that's the place where pool boiling happens because of the reduction in pressure. And at these locations, temperatures can possibly reach to very low level. And in this mock-up case that I show, here we are basically getting into a very unfortunate situation wherein we are basically got into the left part of your hydrate curve. And that basically suggests that during the operation or even the restart, if we were to see such situations, you can end up having hydrate formation problems. And if you were to do that, you should have right strategies to mitigate this problem, namely dehydration through addition of some hydrate inhibitors or even pigging. So I would like to end my talk here to conclude for commercial deployment of us, for successful deployment of CCS technology, safe, reliable operations, very important. And typically, if we are transporting CO2 under 1,500 kilometers, pipeline transportation is something which is very feasible. And when it comes to designing your pipelines, you should be aware of what your CO2 stream composition is, and you should also factor in all the transient situations that can potentially lead to flow assurance challenges like hydrate formation and water dropout. With that, I would like to end my presentation. Thank you.
Thank you, Partha and Abhijit. That was quite insightful and a holistic view of transportation for carbon dioxide. Moving on, another bit of trivia. The whole CCUS story is at crossroads of geopolitics, right? And what I mean by that. So if you look at countries like the Middle East or US, their definition of net zero uh, primarily revolves around scope 1, scope 2, not so much on scope 3, right? And that's why CCUS gives them that edge of continuing to rely on fossil fuels for their energy security, for their economics, at the same time showing decarbonization. We, of course, are at the crossroads because we still rely majority of our energy imports. And so for us to even look at developing CCUS at scale, we will have to think of how to even start with the extraction, exploration, and reservoirs. Thankfully, we have more than 3 gigatons of reservoirs in India. That's what the study says. Question is, how do we make use of those and translate into a global scale on CCUS hub? To talk about this and many more, we have Vishnu, who's going to talk about what it takes on the supply chain side, the equipment side, and market opportunities globally for CCUS. Vishnu, over to you.
Good day, everyone. So today we will go through the growth and challenges in the CCS market and its supply chain. Okay, so as we know that CCS technology is becoming critical for the decarbonization and also, to reduce the greenhouse gas emissions and achieve the climate goals. So today I'll walk you through what is the outlook and the spending of that and the supply chain dynamics and cost trends that is impacting the overall sector. So let's look at the outlook. Currently, the decarbonization goals of the suppliers, the operators, countries, and the industries across has led to a huge pool of projects announcements in the last 4 years. And if you look at the forecast, like in the couple of next years, majority of this demand is expected to be, coming from the North America, Europe, and Asia Pacific. And however, all these announced projects, it is not easy to translate into, operational. So we will see a lot of hiccups during the journey. We can see the cancellations, delays, and even suspensions as well. So if you look at the operational projects right now, there are roughly 200 operational projects, including pilot, small and large scale, and that cumulates a total capture volume of 72 million metric tons of CO2 per year. So all these projects, most of these projects, they work on a single, project framework where the one party takes care of right from capture to transportation and then storage as well. So what we are seeing during the forecast is this will be dismantled. So we can see more segmental type of frameworks and multiple parties will be in the value chain that takes care of capture, transportation, and storage. So if you look at the transportation and storage projects, hubs type of models as more, they are trying to create a commercial based model and provide these services to the emitters for the small scale and pilot scale, where they have, less options to invest high on the transportation and storage side. So in that case, what we are seeing right now is most of these hub-based projects are around North America, Europe, and Asia Pacific. So, as these environments create a successful, transition of the projects, but if you look at the FID, the projects are moving in a very slow pace. So, in last couple of years, what we can see is like 31 visible projects in the FID that has translated further to the construction and operational. And most of these FIDs, it's not easy to announce for any project to have this FID, because if you look at the barriers in this industry, what we faced earlier, there are like huge cancellations and suspensions as well in the market. So, and these cancellations and barriers, they vary across region to region, country to country. So if we talk about unfavorable economics, like in 2014 and 2020 downturns, this has become a key concern for the integrated projects where they take care of the complete value chain. And this is mainly we observed in North America and Europe. And if we talk about regulations, this is primarily a major concern in North America rather than other regions. So you can talk about the Class 6 wells license and also the pipeline permissions and the interstate collaborations across here. So easing the policies and also the process has to be, the time frame needs for the process to be minimized to see the scale into the adoption. And the next, on the funding part, Europe has more concerns on this in the past, but during the forecast or in the future, we can see funding is not going to be that major issue because of the regulatory and incentives, support to most of these projects. So this is based on, we have a cost estimator tool. So based on that, we did analysis on the capex for most of the projects. So what we see is spending across the value chain will be dominated by the capture facilities. However, transportation will take place, significant value in the future because of the hub-based projects which connects the multiple emitters to the transportation infra and also storage. So we can see more investments and more spending to occur in this stage. And if you look at the project status right now, majority of the projects are still in the early stages, like announced and feasibility stage. And these projects have high chances for the cancellation and also delays as well. The high inflation and the interest rates, that creates a negative sentiment for the investors to invest, especially in the large scale CCS projects, unless they see a value in terms of economics. And in terms of, advanced and late stages, right now they are at the very minimum, progress what we have seen during the last years. And as in 2024, in the last quarter over there, we have seen a lot of projects that came into FID. So in upcoming months, like in coming like 3 to 6 months, we can see a lot of announcements in terms of equipment purchase and the construction start for these projects as well. So if you look at the cost components of this capex for multiple industries, at the bottom you can see the increased CO2 concentration from industry from power to ethanol. So first thing is equipment. Equipment is a key capex consumer in most of the industries. However, the spending over here varies from industry to industry. Suppose if we talk about low CO2 concentration industries such as power, steel, and cement, they are like more capital intensive type of projects. They require right from the columns, absorbers, strippers, heat exchangers, pumps, compressors, and turbines. They need a lot. However, when you look at the ethanol and natural gas processing facilities, they already have inherent acid gas removal systems, which will decrease the amount of investment that we need for the capex part. So capex on the capture part. The investments they need over there is on the transportation and storage. And when a hub-based commercial model comes into the picture, these industries will have a good amount of advantage because they no need to invest in those areas that can save a lot of capex to them. And the second part is materials, and these materials like materials in bulk such as that required for construction like steel, concrete, piping, and other stuff. And this particular segment, it varies from country to country, region to region. The local policies and the supply chain and the geopolitical things that drives this particular market. So if there is any issue in the region, few days back we had tariffs on steel and aluminum in North America. If that type of things comes into the picture, it has overall delay on the projects and also projects capex escalations as well. And the third thing is construction. So we require huge in terms of labor and engineering to complete these projects. And these projects takes like 3 to 5 years to complete. It depends on the scale of the project as well. So for the construction here, if you look at the low CO2 concentration areas like power and steel and cement, they require huge time to take the things complete compared to what we required for the ethanol and natural gas processing facilities. So this is here we talk about the state of supply chain. So to understand this, we created a secondary data market based on the available data like orders, backlog, inventories, raw materials, and finished goods, workforce, and lead times of the equipment as well. So we generally track like for 200 suppliers, and we create a suppliers manufacturer index. So when you look at this index, which is like green bars in the graph, so they try to adjust with the how the demand in the market flows. So we have downturns in 2019. So what they did is they reduced some of their facilities, and they closed facilities as well. And other side, they reduced the workforce, and it has impacted the profitability of the companies as well. And slowly they reopen the facilities and increase the manufacturing things with the rise in demand for these equipments. And however, going to the forecast, we don't see sufficient expansion or plans from the suppliers, because suppliers are still in, they lack the transparency of this project's progress. Uh, because they already gone in last 10 years, they've gone through like two scenarios where they faced a lot of concerns, and they did a lot of reassessing their strategies, and they don't want to build further high and look at, if any downturns happen, what will happen going forward. So on that, we have a CCUS demand index as well, and we have scenarios like base, mid, and high case scenario. And base case is something, which is like operational projects, construction, and the projects which achieved FID. So under this base case scenario, we won't see any concerns on the supply chain part, and everything will be smooth, because the demand reduction from the oil and gas sector will offset this pressure. However, when the mid and high case scenario comes into the picture, then we can see a lot of issues in terms of procuring raw materials and the supply constraints, and we can see huge in terms of lead times, and even the cost could escalate for the equipments. So till base case it is fine, but if mid and high case comes into the picture, then we can see a lot of concerns over there. So on the cost trends, like we need to look at, for the equipment cost trends, like one is the raw materials, and the second is the salary of the labor and the engineering part. So engineering part, the salary trends to be more inflated compared to other areas, because the workforce required for this industry is also similar to what we have for the renewables, oil and gas sector as well. So we'll have more competition over there, and in the same way, we can see escalations of, the salary trends over there. However, in the raw materials case, especially in the steel, so in last year we saw lot of plants that are in shutdown, especially in the steel, especially in Asia and Europe on the steel market. However, going forward, we don't see any terms of revival in these particular facilities, as the demand from the market is not yet clear in terms of volume. As as I told you earlier, US had this 25% tariff on steel and aluminum. This could trigger some sort of opening facilities in the China, where the cheap prices of the steel, they can take advantage of that, because the suppliers cannot accommodate in a way uncertainty, the tariffs that we have seen. So they take some time to reorganize their strategies and proceed further to procure the things. And on the equipment index, so the impact from the raw materials to be minimum right now. However, the assembly, fabrication, management, engineering, and the labor rates, that will impact the overall equipment trend. So we can see inflation like 3-2% from these specific things that escalate the overall cost trends of this equipment. So this is the heat map. This is interesting heat map, because it provides overview on the suppliers and the operators and how they collaborate in terms of procuring the things. So till 2022, if you see, most of the things are like in the purple color, which is the weakest supplier force. And the orange is like, the strongest supplier force, where suppliers have an advantage in terms of, they can have the operating margins, whatever they required. So once the base case scenario, this is as per the base case scenario, if the mid case comes into the picture, you will see complete, orange on the right side for the forecast. So, and the key concern in terms of in 2025, what will be is the, labor tightness pool. Because if the immigration and the concerns, what we are seeing right now, if it is more than what it currently has, then we will definitely see the labor tight poolness, and the industries which have intensive labor requirement, they will be first impacted by the things.
Thank you, Vishnu. This was quite insightful. The kind of modeling you've done on the entire supply chain is quite interesting to see. Next, we have Nishevita. Nishevita is going to talk about the membrane technology for carbon capture.
Good afternoon, everyone. Thank you for the introduction and inviting me on the stage. So one advantage of being the last speaker of the session is that the stage is already set. So my topic of the day is pioneering the energy transition through a membrane technology, which we have done for the world's largest offshore CCS project. Okay, so the agenda is going to be, I would like to set the stage by talking about natural gas and the treatment and CO2 removal, and followed by different technology selections and going in deep into the membrane technology, followed by the case study. So I would like to tell why we have to remove CO2 from the natural gas. Definitely we all know that it is an important thing to do as a part of treatment. We would like to achieve the pipeline quality gas, which is less than 3% CO2 in most of the cases. And as a result of it, we would want to increase the heating value of the gas, reduce the compression cost, avoid the corrosion of the pipes, and thereby allowing us to select a carbon steel pipe. And definitely the last 2 points are something which we are talking about in the recent times, using CO2 for EOR, which is enhanced oil recovery, and carbon capture and sequestration, which is the topic of today. I would like to thank Mr. Nekunj for setting the stage already by talking about the technology options for CO2 removal and using it for reinjection. But thank you for leaving the membranes out for me. So what are the different key factors what you will be looking for in a technology? So first and foremost, it should be a reliable technology for us. And second, we need less capex and opex when we want to, select that technology as a preferred one. There should be ease of operation and also low maintenance involved. So when we are going to have different gas compositions and feed conditions, that technology should be suitable. And finally, the technology should allow us for turn down and also have different operational flexibility. Having all these criteria in mind, let's see why we have to go for membranes and when. So as you can see, membranes will be a compact and modular in design. You can handle flexible design conditions for wide various range of operating regions, and it has no chemical process involved. So like a solvent absorption method, there would not be an issue of foaming. And finally, no utility requirements. I just put there a minimum utility requirement because the membrane itself can be considered like a utility, right? It needs to be replaced after, say, 3+ years. We have seen even more, but I would like to put that as a ballpark figure. So having said all these things, we can think this would be a best option for CO2 reinjection purpose. Why? Because the CO2 which is coming out of the membrane would be dry. You don't need to dehydrate it. And also we can operate that, a membrane such that the CO2 stream is operated at a higher pressure than what it gives out of a solvent-based process. So this figure will show you how much, broad range of membrane operation is available. Especially, it's very good for a bulk removal. What I call hybrid over there is when you have an amine system after a membrane unit for getting it down to ppm levels, which definitely the membrane cannot do. So this is just a microscopic view of a single membrane fiber, which is a hollow fiber, what I have shown here. Typically, if you want to describe a membrane, you would want to see high selectivity, meaning you will have to have less hydrocarbon losses through that CO2 rich stream. So pure CO2, low hydrocarbon losses, and high flux. High flux means you are able to give low membranes but get better removal of CO2, meaning low capex. So there should be stable long-term permeation properties as well, that it should not decline over time, right? Then finally 2 points, which it has to be chemically resistant to any impurities and also have a good mechanical stability. So let's just quickly go through what is this membrane technology process, what is the background in chemistry. So it's basically solution diffusion process. As you can see, the membrane allows the permeation of CO2 majorly. Very less quantity of methane also can permeate, and that depends on 2 factors, as you can see on the screen, solubility and diffusivity. When I talk about solubility, it is the ability to dissolve into the membrane material. So more soluble components will permeate quickly through the membrane. When I talk about diffusivity, it is related to size. So any small component will be permeating quickly. So both these factors play an important role in membrane separation. As I can, in the left side, you can see a drawing where I can show that H2S, CO2 and methane are in the similar range of size. So that could be the reason why you can see a little bit of methane loss through the membrane in the permeate. So this is another just a pictorial representation how the hollow fiber would be looking like. And the hollow fiber, what I'm talking about, is made of cellulose triacetate. It is a naturally occurring polymer. And as I already mentioned, it's a hollow fiber configuration. So very unique thing about this membrane is it is an asymmetric membrane structure, meaning the outer will be a dense layer and there will be a porous support structure in the beneath that. So in the previous slide where I showed the microscopic real image, you could have seen that the outer structure was a thin layer and there was a porous structure beneath it. We can imagine that to be like a skin. How these membranes are put together is thousands of such individual hollow fibers are just bundled together parallelly and they form a single membrane element. Sorry, I'm not able to move. I'm not able to move the slide. Can you help? Okay, sorry. This is basically how the membrane science is to technology delivery, how we are doing it. The first, as we already saw, it's the science of solution diffusion transportation, and then you have these asymmetric hollow fiber membrane element which are made by combining thousands of membrane fibers together to form a single element, and they are woven together to form a module, and after that those membrane modules are put into vessels which we call as housings, and based on size, if it is small, we call it tubes. So after those are installed in these housings, they can be just installed in modules, as you can see in the last picture. So I would like to briefly talk about different orientations what we have in terms of the vertical and horizontal orientations. And there are vertically mounted orientations which will be inside vertical vessels which are called as housings. So they have a cross flow mechanism. As you can see, the feed gas enters in the in the middle and the permeate gas exits in the bottom. The central hydrocarbon gas collecting it's actually a perforated central tube through which the non-permeate, which is majorly the hydrocarbon, gets collected. So this has a cross flow mechanism, and we are having this vertical arrangement in 5-inch, 12-inch, 16 and 30-inch diameter bundles. So they are basically used based on the flow rate, composition and all, and we are usually saying 16-inch and 30-inch more in commercial side. And this vertical membranes, I would like to mention, they are very they're very comfortable to be operated when there is a little bit of hydrocarbon condensation environment. And this is the horizontal construction. The horizontal construction means if we are just making an 8-inch tube or 8.25-inch tube. They have a counterflow mechanism, as you can see, the feed gas and the permeate gas configuration in the drawing. And they are basically available in 8 and 8.25-inch, as I said earlier. And in this, there is a construction difference where the central core tube will have permeate collection. But otherwise, all the membranes are the same. It's just the construction which is different. So just to put a quick comparison of vertical and horizontal, so usually horizontal is good for low CO2 in the feed and low flow rate operations and high pressure applications. Vertical, we have been very successful when there is a high flow rate application and to overcome footprint limitations. So these are the favorable membrane process conditions. So when you have inlet CO2 from 10% to 90% and the pressure is below 70 bar, the temperature is below 45 degrees Celsius, and when gas flow rate is higher than 2 mm SCFD, membranes can be really a good option to consider. So we do have other membrane installations which is effectively implemented outside these regions. We can be analyzing it in case to case. So this is a study about the offshore CCUS project that we executed last year, and the right side is the module. As I said, how compact it looks like, you can just look at it. It is a module that we delivered. So what is the problem statement on this particular project is that the natural gas treatment plant was already existing. It was actually sending out gas that has to be flared that contains 73% of CO2, but the rest was all hydrocarbons. The company did not want to do that owing to the net zero initiative. So the problem statement was that they have to recover the hydrocarbon and re-inject the CO2. The solution was like we have to find the technology which is more suitable to do the CCS, and we ended up with making our membrane as a suitable technology for making the pure CO2 re-injection into the depleted offshore well. So this is the condition what we had. The CO2 concentration was 58 to 73%, and the pressure was 45 bar, temperature was 45 degrees Celsius, gas flow rate 195 to 256 mmSCFD. These were all very favorable for our membrane operation, as I showed in the previous slide. So this was the objective, and basically the objective was to definitely recover the hydrocarbon from the gas stream that was actually being prepared to be flared. And we had to reduce the CO2 emissions by re-injecting into the depleted well. The challenges was we had to do a lot of capex reduction, optimize the OPEX, as well as do a better technology evaluation, and we landed up with membrane being the best technology. Sorry. So basically, it's just the same what I said in the previous slide. We had 73 mole percent CO2, and the recovered hydrocarbon stream was basically sent back to the original existing unit, which was a phase 2 unit. It had CO2 of 22 mole percent, and the other stream, which was a permeate stream rich in CO2, was 90% pure, and we had prepared it for reinjection. This is just a pictorial representation of what we actually did. So the outcomes, quickly to go through them, we actually used a horizontal membrane on this application, and we had 3 into 33% of capacity based on the turn-down requirements specified by the client. We had optimized the hydrocarbon recovery, and this is the main point. We had done a reduction of 3.3 million metric tons of CO2 emission per year, which made it the world's largest offshore CCS plant. And the capex was optimized when we were able to reduce the operating pressure, and thereby the footprint was also optimized. The life cycle cost analysis also was better here, because we did predictive, we actually could support the result with benchmark projects, and we were able to prove the readiness level of the horizontal membrane to be implemented. The total cost of ownership advantage was always there, because we had given predictive monitoring with the project. So a step forward was that the client was able to go forward towards the net carbon emission by 2050. So these were the key differentiators. We had been able to do this design optimization by reducing the pressure, and we had given the modular skid with reduction in footprint and weight, and the total cost of ownership benefit I had already mentioned was existing in this project, and we had enhanced customer experience by involving them from a very early stage and did process optimization. So to just conclude on this, I would just like to mention that membranes have been just proved as a preferred technology for pre-combustion CCS projects. And it has a very good technical integrity and cost competitiveness when compared to the other technologies. And it has flexible configuration to suit client requirements like vertical and horizontal. If there is an existing facility which has a horizontal setup, we can retrofit it. And it has proven highest plant availability. We have the earliest plant operation since 1983, and it has more than 98% of on-stream plant availability. So we are able to fully digitalize the designs by enabling predictive monitoring, which will give a better prediction of how long the membranes are going to be performing at the expected results, and give the optimum outcome. So this has helped in total cost of ownership as well for the clients. So that's my conclusion, and thank you for listening to me patiently.
Thank you, Nishavita. Thank you for bringing to life what global CCUS, at least the carbon capture plant would look like, and the economics for it. So thank you for that. As we come towards the end of this session, I think, and reflect back upon the kind of innovation, advancements on technology and the supply chain readiness for CCUS, I think it's quite heartening to see that over the years we have come to a stage where we are talking about successful pilots, we are talking about bringing life a scale project. And we hope the next time we are here around, we will have more talking points, more insights, and maybe a prototype of what a CCUS hub would look like in India. So thank you all for joining us.